let's get started. The view you guys, besides all the Excel file, the computation, can you see that so far we can see the world using a horizontal line above and below the subway station view, or we can have a regression line with a slope or a vector, and then a bunch of data pulling that vector, to try to make them equal based on the sum of square to make that vector right in the middle of all the data points. Okay? If you have those two views to see the data, that means that at least you have the big picture. And computationally, if you can get your spreadsheet right, then
did you post that regression learning PowerPoint yet?
Yeah, it's there.
Under what?
Under lecture 4.
I don't see that. Lecture 4 is not published. Yeah.
Oh. Okay. Okay. So you can download it now. Yeah. Sorry. Yeah. TA or whoever coming early before the day, knock on my door and said, publish it. Sometimes I update the lecture notes, but I forgot to publish it. Okay, so those two different views, the regression lines view or central stations view, are at least 60 to 100 years old. Today I'm going to talk about another view, which is machine learning view. Just learning and keep updating the stuff. And can you live without this for a design block experiment? Yes. And especially when we talk about response surface, I'll give you the solutions. So you don't really need it. But on the other hand, I feel guilty if I don't explain this to you because what is hot in the job market is not just know how to figure out the ANOVA table, how to do the regression line. You need to know how to use the new data to update your regression line, your ANOVA table. And I think I already demonstrated this a little bit last time, is that not all the data points are the same things. I used the outlier to demonstrate that I can make no regression to regression or make regression to no regression just by adding a couple points. So you know that you can have tons of data points, but not all data points are equally important. There's another way to think about this is, what will be the most common sentence you write in your capstone projects or your senior design at the end? Oh, we did this, we did that, but we didn't really find anything significant. However, okay, we probably will find something if we have more data. People always say that I need more data. And usually, most of the reviewer will let you go with that. I usually don't. Because I would say, then tell me what kind of data you really need, right? Random number generator is quick. You can tell not all the random number play the same role in your ANOVA table, in your sum of square like a fit. So there are smart data, there are dumb data, okay? And that's part of the reason. That's the kind of intelligence that you need to demonstrate in your job interview. Because if you just tell people you need more data or more catchy phrase, this study throw a light to future research. You know what does that really mean? You are BS con artist. You did not do anything. And so what is very important is don't fake it. You fake it, you just let people despise you. If you said, I discovered something, it should be real. You fake it, senior design at the end, you guys put the suit on, put the ties on, put everything, and give a presentation. Does that really mean you really discover something, you design something? Sometimes it's not. Okay, so what I'm saying is the computation is important. The finding the ANOVA table is important, but not everything's equal. So learning is really about trying to figure out what is really going to make the difference. If you can just tell me what's going to make the difference, okay, or I show you the machine learning, you just said, well, machine learning, I plug and play. So what? Then when you stand side by side with a Clemson grad, a NC State grad, you need to let the interviewer say that, no, we're not going to hire those two, we're going to hire you. Where's that confidence coming from? Okay? It's not because you can talk without accent or something. It's because you can show people, you can find the evidence, you can defend your decision based on numbers. Okay? If you cannot defend your decision based on number, then yeah, keep faking it. Okay, this is something I'm talking about regression line, and we already done this before, and showing that, okay, if I have a lot of data points, I can figure out how to fit everything. But then, when you try to fit everything, sooner or later, people will say that what is overfit, what is underfit. In a polynomial, second order, third order, what will be the right order? For example, like the data points here, if I use the green curve, a second order, I definitely, will fit most of the data points. But the likelihood to cover this point, it's not going to be possible unless you increase the polynomial from second order to third order to fourth order. And of course, you can have the n-1 order, n is a number of observations to fit every data point. But then it's overfit. So sooner or later, whenever we try to add data points, we try to add the level of complexity of the model, we ask ourselves is, for example, right now, how many of you really think that we need this Ember model to describe all our data points? Okay, and then how many of you think that just use a straight line, red line, is good enough? So one is underfit, one's overfit. So we're need to at least figure out later using the sum of square and says that, hey, do I use all my sum of square wisely to explain the things I try to explain? And so that will dictate the order of the model. Okay, suppose I have 5 data points, okay? And then I already showed you last time, or at least 2 lectures ago, find your denominator D with only x involved, and then all your parameter is x and y involved. So x and y is the area divided by the x only, it's almost like a square. And then you figure out that ratio. That ratio is how much x increase and xy increase with it. Area divided by the base, that's your slope. And so we use the least square algorithm to figure things out. And now let's talk about how to improve that. And how to improve that, that's machine learning. Basically, I don't need to do that by looking at it. I let the machine evaluate it. And when the machine evaluates it, you need a step size. And every time you basically look at whatever your observation minus whatever you have, and then you figure out how much the improvement should be. And as usual, I think the best way to learn this is learn through a regression model, learn through an example. So in Excel, since I give you the data, my PowerPoint, all you need to do is right-click on that table, and then say open the spreadsheet. You guys know how to do it? No. Okay, one more time. See the PowerPoint, you have that? Right-click, okay? And then it said worksheet object. I basically bury that worksheet object and just open it. Okay? And this is a simple example. And in a simple example, I said that, I would like to find the slope. And the slope between x and y, I can just say, hey, find me the slope is 1.98, right? But this 1.98 is just using the least square or your D way to find it. But what if I said, I'm not going to allow you to find it this way. I need you to use the data point to learn from it. So iteration by iteration, I can start from 4, I can start from 5. And then, of course, you look at the iteration after iterations. Sooner or later, you'll reach some point. Okay, let me go back to, say, start from 4. Okay, so you can tell if I start from 4, the error will be drop to 2.19. And if I start from, well, I can keep going, okay, what is it? But if I start from, say, 3.5, so sooner or later, I should get closer and closer. Let me copy paste a few more iterations, you will see that. Okay, it will drop until it gets closer and closer to 1.98, the true answer. And okay, I'm gonna ask you the questions. Since you guys already learned how to use dA divided by D, dB divided by D, or use X transpose X, X transpose Y, X inverse, X transpose X inverse, X transpose Y, and well, you'll find the answer. Or you can just plug in Excel, get the slope 1.98. Why we want to do it in an iterative way? Try to improve, and try to find the answer that way. If I can find the answer directly. That's the truth about machine learning is the following. How many of you ever watch YouTube? Do you think YouTube is like playing a movie, update every screen, shot frame by frame? How many of you think that that's how YouTube give you the movie? Do you think that will be a smart way to provide, I have 30 some students, 35 students in this class. Everybody watching a video. Then YouTube need to provide 35 video. And not to mention now the whole world is using YouTube. Do you think that's a smart way to upload the video?
Probably not.
So what will be a smart way to do that? Here, if I have the screenshots right now, say, here's what I'm talking about. What I did is I only changed the number from 3.5 to 4. And something changed, okay? Does everything change in one shot, or some stuff in the background never changed? Say, the James Bond movie is coming out pretty soon. When they have the videotape, do you think the movie, every frame, James Bond is moving, the actress is moving, the background is moving, everything's moving, or a lot of time only few things move, but the foreground, background actually pretty much the same. So what YouTube did, or a lot of machine did, is this. They figure out that among all the things, if there's no change, keep that part of the model or that part of the regression as it is. So in other words, I give you a regression, there are 10 lines, 10 points, right? I only need to upload what? Those points actually got updated. If those points not updated, leave it as it is. But if that's the case, if you use the conventional regression line approach, that means what? You have to calculate x transpose x, x transpose y every time, even though a lot of times say I have, 2,000 pixels or 20,000 pixels. There are only 10% changes. The rest of the 90% never changed. You upload everything and do the matrix computation, that's wasting time and money. So that's why machine learning is important. So here I'm basically show you how this is done. Here, if I have an x, I have a y. And then if I set the slope, let me say that I log the intercept, okay? So every time I can say that this equal to F9 is...
So you're given your x and your y, correct?
Yeah, the x and y, we're not generating any data, just give you the data. So I will give you some example one more time with the slope. But what I'm trying to say here is, first, okay, every data point is y minus the slope times the x. So that will be the differences between the two, right? And you can add a constant if you want to. So every data point is, hey, what is your y and what is your prediction of y? And so here, every row you can consider is what? It's the difference between my prediction y minus my actual y. So yi is my actual y minus my w, 4 times x. So first one, 2.1. Here, let me write it somewhere else. 2 equal to 2.1 is my actual y minus my current slope, my w, I believe is w, is that, times my location x is 1. And that will give me negative 1.9. Follow me? So every data point here is, by using this is what I believe the slope is going to be. And then I can figure out the predictions. And then when I do a sum of square, okay, and average, I can have the error term. And what's my next step? My next step is, hey, obviously 4 give me so much differences. So let me try to improve a little bit. So add a little bit. How much a little bit? I define my step size alpha. or here should be alpha. Okay? Define my step size alpha. I can say that what would that do to me is, so my new W or omega n plus 1 equal to my O1 plus a little bit of changes. And where that change is coming from? My step size, and then my prediction error and my magnitude. And just keep doing this again and again. You will see that every time is, hey, I'm at 4. How's my error? It's 0.08. Well, can we cut it down a little bit? So add in the opposite direction, add in an opposite direction. So you see these things drop, 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 and then you're getting closer and closer to the true slope, 1.98. Okay? Let me use the example you guys are familiar with. Pure regression. Okay? So this is least square algorithm. Okay. One way, your homework probably based on slide 5. Okay? So, start from this. What is my error term? Can you guys see it? Oh, shoot. How about now? Still no good. Okay. Okay. So, sum of square error is my prediction y hat minus my actual observation yi, right? Agree? And then, since I need to maintain all the differences in positive, so I square it, and then take the average. That's my variations from my actual, so what we call that? Prediction error, right? Or sum of square from the line. And take the average. And the things, J, we want to minimize or maximize. If I want to have a nice regression line, J should be maximized or minimized. Minimized, right? Because we want the differences between my yi and my y hat as close as possible, right? And the other things is we learn from our previous study is that, so any things that will cost, what will cost this J big? Any data points, any y hat and yi are far, far apart. Remember the example I give is, here's the table. So that table is, a line of table is my regression line. People sitting on the opposite side of the regression line. And then everybody is saying, hey, come closer to me, come closer to me. Some pulling from that direction, some pulling from above the line, some pulling from below the curve. Okay, who got more power to pull? The one far, far apart, right? So when we pull that, what we're trying to do, every data observation. Here, when you, the last one, the guy, yeah. Here is the regression line behind you, right? And why you want to pull that regression line closer to you? Why you want to pull that y hat closer to you? Your yi, I number 35. Why you want to pull that closer to you? Because if that line is closer to you, your contribution to the J will be smaller, right? So everybody's doing the pull, pull, pull. Above or below. Does it matter? No, because we square it, right? That's the sum of square coming from. Okay, so J can be considered as big. Can you guys visualize what I'm talking about? Right? Above the curve line, below the line, everybody's trying to, every yi is saying, get closer to me. And so beta 0 and beta 1 x is my y hat minus this beta. So this represents this. Still the same thing. Find me some beta 0 and find me some beta 1. So I can get this line can be closer to my yi. That is the the temptation of every observation. So this objective function j, how to find a good solution is partial derivative equal to 0. And if partial derivative equal to 0 for beta 0, and you pull the 2 over here, so it becomes 2 of this, or 2 of this. And then when you've done this, you said, hey, it's related to beta 0. Okay? And, oh, I made a mistake here. Here, there's a term you need to put in, is times xi. Why? Here. I wonder I can do that. No, I can't. Watch here. Partial j, partial beta 0. Beta 0 is by beta 0 itself, so as it is. Here's the line. But if it's for beta 1 xi, so I have xi here, so I need to do a derivative 2 times this and times xi. So that will end up looking like this. Partial j, partial beta 1 equal to 2 y hat minus beta yi times xi. Can you see that? So if we have these two equations, both are saying the same things. Hey, get closer to every yi by manipulating my beta 0 or manipulating my beta 1 such that j could be as small as possible. Then we can use the example I showed you before. Again, mu is alpha here. And then I just said that every step, I have an O beta 0 and O beta 1. I need to improve by doing this. So here, let's do it step by step. This time, be very, very careful, okay? First, I have 5 data points. And then I have 5 outcome, x and y. This is easy, right? Everybody see that? And then you can find an intercept. You can find the slope of this 5 data point. So far, so good? And you guys can figure these things out just by plugging this or using any solutions we had before. So far, so good? So you know the answer from our previous exercise, how to do this, right? Now, we're just saying that I want you to find the intercept, I want you to find the slope through learning. So, learning, I start by saying that, okay, I need to start from a guess. Learning always starts from a guess, a guessing point. And I guess is 6 and 4. If you don't like 6 and 4, you said, oh, I would like to guess beta 0 is 6.2, beta 1 is 4. That's fine. You just guessing point. Later on, when we start talking about response surface, I'll tell you there are some intelligence involved in how to guess. But right now, I just want you to learn the iterative approach. So far, this is my initial point. 6, 2, and 4. So every data point should equal to, every observation should equal to beta 0 plus beta 1 times x, that's my prediction, minus my y, that will be my error term. Agree? So I have error, 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 error. First of all, I have a lot of big error, right? Except what? The last point seems pretty good, right? The error is small. But since right now we're not using some other intelligence, we just said that all errors count. Then we just said that, oh, here are the errors, okay? And of course, if you want, you can even do a sum square here. The sum square here is the total error I have right now. And then if you look at this, do you see the sum of square error is dropping? If the sum of square error is dropping, that's good news, right? And of course, later on I will say that we need other intelligence, because sometimes we'll get trapped in a local optimum and not the global optimum. But right now, we just, for first experience, we just said that error is bad, and then I'm improving my error. So how to improve my error is this: original intercept and original slope is 6.2 and 4. I said it's no good. I would like to change it a little bit. How to change that? I'm basically doing this. My beta 0, my new beta 0 is equal to my old beta 0. So look at here. My second beta 0 is a function of my 6.2. So do you see 6.2 play a role in estimating 5.14? Yeah? That is my beta 0 minus a step size. Oh, on the step size here, I play a trick. Okay? Here's the tricks I play. I come up with a alpha equal to 0.05, and then I'll say that, hey, I'm only using 40% of it. So here's the 40%. If you don't want to use 40%, you can say that I want to use 60%. So you just change that. So change one number. So you can call this 3.5 step size discount. Okay? So here, equal to my current beta 0 equal to my old beta 0 minus my alpha times my discount. So that is this part minus this part. Okay? Divided by n, 2 divided by n, and then sum of all the error term. So you sum all the error term together. So I'm basically show you these equations I used. And then of course for beta 1, since it's the slope, I need to involve x. So it's x times y. Yeah?
So your 6.2 and 4, those are also going to be given to you, like a base?
You mean in the homework, or in the homework? I haven't decided yet. I could let you start a starting point.
Oh, like let us pick a intercept?
Well, like let's play a game here. Give me a starting point. Beta 0 and beta 1.
4 and 6.
And I'll say 4 and 6. And then you just keep seeing these things drop, or increase until you find a good data point. Okay? And, well, now the more I think about it, I probably will give you a starting point. So, at least find some convenient point to start with. But what I'm saying is, in real world, real machine learning, Google is doing it. Usually, there are some strategy to pick the starting point, but it could be anything. Okay? Okay, so first thing first is that when I pick a new improvement, beta 0 equal to new beta 0 minus this and this, it looked like our least square in disguise, right? Yeah. So there are things involved here is I'm keep doing this, sooner or later, hypothetically, look at the answer. I'm getting closer and closer to my real slope and real intercept. Okay? Right? My real slope and real intercept is this. After, over 100 iterations, I'm getting closer. And you know what's the bad news? Is that sometimes, because if you don't have a stopping criteria, you find a good answer. Yeah, here is another story that if you took my reliability class, you heard this one before. I think people give credit to Lincoln. President Lincoln tell a little boy, "Hey, do you like Go Nugget?" And the little boy said, "Yeah." So President Lincoln said, "Okay, here's the trail all the way down to the lakes. You walk along this trail. Find the largest pebble you can find, and I will reward you a Go Nugget based on the size of the pebble." The little boy said, "Oh, that's good, right?" So Lincoln said, "But under one conditions, you have to make up your mind. Once you pick up one, that's it. You're not allowed to say, 'Oh, I find something bigger.' Drop and then pick another one." So in other words, is that it's like life, right? Choose your school, choose your mate, choose your spouse, choose your career. Sometimes there's too late to make another change. What you decide is what you decide. So guess what happened to the little boy? He walked out of the wood, the trail, empty-handed, with tears in his eyes. Why? He felt like, man, there's something bigger. There's something bigger, and wait until it's too late. So if you're a system engineer, you try to find the optimum solution, iteration after iteration. What will be your strategy? Avoiding eye contact? What will be your strategy so you won't be that little boy coming out with tears?
I would guess.
Huh?
At some point you have to say good enough is good enough when you're looking at your...
So what is that rule then?
I'm not sure.
Can you say that, okay, let me sample the first half of the trail and then come up with a histogram. And then my decision rule will be as long as 90% above the histogram is good enough. And that'll be a rules, right? And what does that got to do with this machine learning things? Is later on we'll talk about stability of my learning. If you see the sum of square here, let me do that for a change. Okay, if I do the sum of squares things, oh, I got it wrong. I already see my mistakes. Is that's good. Okay, the tricks you have here, actually, I got it wrong. I don't have the right answer here. I think I'm going to just explain to you this way. Every time when you come up with the iterations, okay, now I'll use next example to show you. Okay, here is another example. And this time I have even more data points. Okay, and when I have all the data points, so now I'm just using the sum of square. I put it right here on the right side. Okay, so everything's the same. Beta 0 equal to beta minus the step size, and then I have a plot, the sum of square. People just look at this, okay? First of all, can I have my step size? Where's my step size? Oh, I have the same problem again. You guys cannot see it, right? Insert. Okay, can you see it now? Okay, here's the sum of square. Okay, so I put a sum of square from very beginning to this one is really large scale. I did it 1,000 times. Okay, and of course the same things. You have an intercept and slope you can figure out by just using Excel. But then what I'm doing here is I calculate the sum of square by manipulating this step by step. Okay, and then here I come up with a step size, and the step size here say let's start from very beginning. People watch this. Okay, I'm using 25. 1 over 25 of my 0.05. Okay, if I change this to 10, so my step size, if it is divided by 10 rather than divided by 25, the step size will be what? A little bigger, right? If my step size a little bigger, what do you think will happen to my my sum of error dropping rate? Let's play and see, right? Large steps drop really quick, right? Small steps, so let's go back to the small steps. Divided by 50, okay? It will drop very slow. So right now, you don't need to do anything, okay? I just need you to think about a couple of things involved. One question is what she asked. Hey, where's the starting point? Where should I start? Okay? The second one is where you start and where is the directions. And direction is easy, right? Right now I said it's least square. Pulling in the directions will make my error smaller. The third problem is really hard is the step size. Why? Because if you're that little boy, okay, you said that, man, I have to find the biggest stone that's possible. Can you just watch 1 millimeter shuffle gate, 1 millimeter at a time, and sample really slow? Could, but probably when the kids turn 100 years old, he's have enough sample. That's too slow. The step size is too slow. But on the other hand, what if we just use a huge step size? In a single example, all you see is single smaller, say divided by 5. Singles large step size is basically said that, man, I'm just walk 10 steps, really jump, and then figure out whatever I need to figure out, and use that few steps to come up with a sample to build your histogram and decide your criteria. What is the problem of doing that? You rush your decisions, right? You could miss something in detail. So what is the take-home message about what you learned so far is more philosophically. Okay, career, searching for whatever. First, find the right starting points. Or justify your starting point. Find the directions and find the right step size. If the step size is too big, you rush to the decision. The step size is too small, takes forever. Okay? Well, how many of you like to Google and find answer for paper or homework? So far, did you find any homework solutions from my homework? Well, everybody talk about something, but I don't think I copied my own homework, so it shouldn't be the same. But what I'm trying to say here is that that's the things. You Google, you download 100 million possible, hit 100 million sites. How many of you actually using the 100 million sites? Search one by one. Or usually the first page, after 10 search, you're done. You look at the first 10 search outcome, you're done, right? So obviously, when you do Google search, what is more important? You know what you're looking for. If you know what you're looking for, you use the keywords very, very careful. And if you use your keywords very, very careful, then you find the smart search. Okay? So the intelligence is really involved in 3 things: starting point, directions, and step size. Okay? And that's it. So we finish all the view needed to look at all the experimental data. Now we just play with different kind of design. Okay? So here is my old lecture notes. And in the old lecture notes, the first thing we're going to cover is called blocking. Okay? So blocking and lotting square are the following. Okay? In our previous design, we just said that I repeat 3 times. Treatment A, treatment B, treatment C, completely randomized. But in the real world, sometimes there is not enough money, not enough time. So the blocking will be like something like this. Okay? First, you said that how many blocks I'm going to have? I'm going to have 4 blocks. So you will have block 1, 2, huh? Okay. How long do you think I will learn my mistakes? Never. Okay, here are 4 blocks. And then say that, let's say 5 blocks. Okay, and each block I can have, originally, if I can have, say, 6 observations. Okay, remember, first thing first is, in the old days, is we just said that, okay, here are 6 observations needed. So I will come up with the sequence and then pay special value. And so first thing is ignore the block and then just come up with the rank or the order. This is called completely randomized design, right? Rank of every observation relative to everybody. Block. And so the experimental sequence is something like this. Okay? But now, if you consider there's a block, okay, this is wrong. What will be the right way is the following. I can only figure out a sequence within block. So what I will do is rank. Hey, I'm running block 1 or block 2 or block 3. So when I run this block, I only figure out that the experimental sequence within the block. Okay? So I'll lock this. So this is called blocking design. Okay? So I'm only running the sequence within the block. And then, in order to do this fairly, sometimes people will say that, well, so maybe I need to randomize the blocking. So you can have another random number. Just say which block I'm going to do it first. and then you log the blocking sequence. Okay, so you will say the rank of this one relative to this entire sequence. Okay? What did I do wrong? Oh. Ay, ay, ay. Okay. So we'll do block 3 first, and within block 3, here are the treatment, and then we'll run block 2, and then block 1, and then block 5, and then block 3. So first decide the blocking sequence, and then decide the treatments within blocks. So rather than organize, completely randomize all of them, we do it partially. Okay? And the guy who figured this out is called Don Fisher. He's an agriculture engineer from Iowa State. Iowa, a farming state. And in the early, I think it's 1940 or 1950 when they come up with all this. And if you ask me the statistics or good experimental design school, guess where are the good experimental design school at the beginning? The Big Ten. Why Big Ten? Iowa, Minnesota, Wisconsin, or Midwest agriculture state. The agriculture states, so they have a lot of land-grant university. So University of Wisconsin-Madison, they have Box, Cox, Draper, Iowa, very, very good in agriculture. Okay, but of course, these days, pharmaceutical company, biological company, very good in experimental design. That's why Carolina, it actually is a very large experimental design, statistical analysis school. You guys know I'm going to introduce SAS. And you look, guess where SAS was developed? NC State, Cary, and why Cary? Triangle Park, Duke. At the beginning, the tobacco industry, the agriculture. Yeah, North Carolina, before the Triangle Park, actually being considered more like a agriculture state. But because of we have Triangle Park, so we're diversified there. But anyway, here is one way to do blocking, and later on, actually, we can have the so-called So sometimes they call it block, and because of the agriculture influence, they call it plot. Okay, so first figure out a plot, and then figure out the treatment within plot. And later on, actually, people are doing the so-called split plot. Guess what a split plot means? You'll have a major plot, and then you have a subplot. So in other words, for example, I can have this, okay, and I'll call this main plot 1, and what I will have, I can have a main plot 2. So, and of course, you only can have main plot 3. And how you do it is, say, I have the main plot left, main plot right, and then I'll have pay special value, and then oh no, I'm going to do it this way. Yeah. So now you can say, oh, I only have two memplot. I have memplot 1 or memplot 2. And then within the memplot, I have subplot. Oops. Here I need to change the number. Pay special value. And then and once you do that, see here is, should I do the memplot here or do the memplot here? And within the memplot, what should I do? Which one is my, how come they're the same? Interesting. Let me try a different random number. I don't like this example because the sequence is exactly the same. Okay.
That's the same again.
What did I do wrong?
I don't know, it's weird.
Huh? Rank of the number. Okay, let me try. Okay, now at least this time doesn't look the same. Okay, what I'm trying to say is when you don't have enough money, sometimes they'll say that, oh, I'm going to do this mem block 1 first year, mem block 2 second year. Within the block, I'm going to do this in the first 3 months, second 3 months. So you separate the space or time or whatever based on the plotting plan. So if you look at the lecture notes here, I basically said that, oh, there are blocks and there are treatment within blocks. And then you can have mem block, you can have subblock, you can have mem plot, subplot. Okay? And so if in a job interview people ask you why you're doing blocking, what will be your answer? What will be your answer? If you're in expert, okay, somebody volunteer. You know, when you out for a job interview, it says that, well, you want to work for Triangle Park, you want to work for pharmaceutical, and they said, why you need to do blocking? What will be your answer? Huh? Slowly, I cannot hear you. Priority? Wrong. Somebody else? Christine? Is Christine here? No? Okay. Tia? Why we want to do blocking? Why?
Variation.
Huh?
Like ensure a variation.
No.
Optimization.
Huh? No. Don't give me any three. The real reason we're doing blocking, put it down. Money and time. I don't have enough money, I don't have enough time. So I have to do it section by section, block by block. But because I have to do it block by block or subplot by subplot, memplot by memplot, remember the first time when I introduced you experimental design, I said I think you need to randomize the trials. And what was the reason I have to randomize the trial? Why?
Fairness.
Fairness. Because, why you go first? Why I have to go last? So now when you do blocking and sub-blocking, the same things. Is since we cannot do it all together, then some will go first, some will go last. Why you should be in the main block, one. Why you should be in the sub-block, one. People will say that, I don't like my location. I like your location better. So you need to come up with a justification and say that I randomize within the block. Okay, so next, let's consider how I have 4 cars, 1, 2, 3, 4. And every car I can use A, B, C, D, 4 different tires. Okay, and then if I use car 1, I have A, B, C, D, 4 tire. Car 2, I have A, B, C, D, 4 tire. Every car got 4 tire to be tried. And then, I can check the mileage, I can check everything. So first thing first is find the tire and tire average. So the things, same things, I already, by request, now I'm showing you all the computation directly. So first thing first, this 16 number, just like the previous experiment, 16 number given, or random, whatever I come up with. And once you have those 16 number, can you find the total? Can you find the average? Can you find the total? Can you find the sum of square? Can you find the this should be the average too. Here, Here, if you use average, okay, so far so good, right? You have average of the tire, you have average of the brand. Everybody good? Okay? And of course, you can have the overall average. The overall average is the average of 16 number. Agree? So, can I figure out the total sum of square? The total sum of square is every number minus this number, right? And then divided by 12 or divided by 16 or 15, right? Divided by 15 because we reduce 1 degree of freedom. So to figure out the total sum of square, one way you can do that, okay? Somebody already answered that question last time, is that you can just figure out the variance of this 16 number, okay? And then times n. Okay? And now let me do it differently. Standard deviation square is my variance. And then if that's the case, it's times 15. Okay? And I'll have that number. Just keep that in mind right now. You don't need to do anything because I'm going to show you in next slide. So you just keep it in your short-term memory. Okay, so here are the sum of square. So, yeah?
What did you do with the standard deviation?
Oh, standard deviation, here. If I have 16 number, standard deviation is everybody minus the overall mean square divided by n minus 1, 15, and square root, right? That's your variance, right? Standard deviation, right? So, okay. Let me go back and just keep the number in mind. Okay, here. Okay, standard deviation is the square root of y minus y bar, the overall central station, but standard deviation, since we estimate the x bar or y bar, so I lost 1 degree of freedom. So it's divided by 15. So I only times 15. The only reason I'm doing this is saying that I'm going to do it the dumb way first, but just keep that cheat sheet in mind. Is there's a quick, short and dirty way to get that done. Okay, how can I figure out my 18.5? Okay, is doing this. Okay, so here, every observation, I can minus the mean, right? And my mean is 12.5, right? 12.06, right? So if everybody minus 12.06 and square it, everybody minus the central station and square it, minus the central station and square it, and then when you sum them up together, that's your sum of square total. Agree? This is not different from what we did before. 16 number, there's a central station, overall average. Everybody minus that average, square it. That's your, how far from your home to the central station, right? Agree? So everybody minus that total average, I get that, that's 80.94. And what she asked me a few seconds ago, how did I get that? I just said, give me the standard deviation of this 16 number, square it, and times 15. I get exactly the same, well, not the same because I have less, yeah, here. This and this are the same. Okay? Okay, so now I have look at everything and said, oh, here's my central station, how far away from my central station. And then next, let me get it done. Next, can I figure out where is my car average? So is my 14 minus my central station. So if I use my 14 minus where is my 1206, that is treating every car. Treating every car is what? A subway station. So if the same subway station is 3.75, 3.75 is 12.75 is this far apart. So sum of square car is the treating every car as a subway station. You get a sum of square car. Agree? And then I can figure out where is the sum of square of the brain. Is treating every brain is a subway station, and then I have a sum of square this. And finally, what is my error term? There are two different ways you can figure out your error term. One is using sum of square total minus sum of square car and sum of square brain. You'll get this value. Just total minus the partition explained by car, explained by brain. The other way to figure that out is, okay, this is the tricky part. I can consider every observation relative to my car subway station. I can relative to my treatment station, but then I'm doing this twice, right? So I need to, when I do this twice, so when I try to figure out everything, I need to add the overall average back one more time in order to get that. I'll explain this next time to you why we need to add one back. Okay, you can consider this, okay? here's Simon, here's the evil twin of Simon. Really is the same person, but, Dr. Frankenstein, right? One Simon is calculate the distance relative to the car. The other is relative to the tire. But in reality, I don't have two observations. I'm using the same observation to the car reference, to the tire reference. So if I do it this way, in reality, my variations in reality is what? I don't have that many levels, so I need to add one overall average back in order to balance it, in order to create that, hey, I can split it now. One central, one car, one for tire. But in reality, it's the same things. So the things that I will give you as a homework is to prove that when you do this, adding one back, you will get the same number as the sum of total minus sum of car and sum of brain. So again, at the end, there's a checking mechanism. You know that you got it right or you got it wrong. But the thinking is, really is one observation dealing with two different types of variations. Okay, see you next time.